The next speaker is Kshitij Tayal from Oak Ridge National Lab.
Good morning, everyone. So my name is Kshitij. So today I'm going to talk about LLM for time series forecasting. So from morning, we have seen a lot of the work which has been utilizing LSTM for streamflow forecasting. But recently, LLM have exploded in popularity due to its ability to process sequential data in parallel. And in natural language processing, people have shown that if you train large enough model with large enough data points, then the model which is learned is more generalized. And in this talk today, I'm going to talk about some of the existing work for time series forecasting using large language models. What are the limitations for environmental application? And what are the work that we are doing in this lab? So we'll start with the introduction and the background. Just I'll spend 2 minutes there. And then I'm going to talk about a couple of works which has been done on time series forecasting using large language models, specifically patch TST and inverted transformers, which are really popular. And then I'm going to talk about how people are utilizing a pre-trained existing LLM for time series forecasting. What are the modifications they are doing? And this is the latest work, which is a person has trained a LLM model from scratch for time series modeling, and they have shown a very good generalizable capability for zero-shot forecasting. And then I will just conclude my talk. So just to give a very brief overview of LLM. So LLM consists of just 4 parts, and these 4 parts are stacked on top of each other. So if we say 700 billion model, 700 or 100 billion parameter model, so most of the parameters, they lie either in the input embedding or on the feed-forward layer. So input embedding in the NLP context, we have a word, and for each word, we have an embedding. It could be 512 dimension embedding, it could be 1024 dimension embedding. And if we have to translate this model for time series forecasting, we have to define the definition of a word in a time series. It could be either a single numeric value could be a word in time series, or it could be the whole time series. We could say this is a word, or we can define a variable called patch length, and then we can say this is the definition of a word in the context of time series. And the goal is the model will remain the same. And the goal is just to define the context of the word and define the positional embedding and define the layers, and that's it. So that's all we are going to do. So that was a very brief background on LLMs. And now coming back to time series problem statements. So we have, basically we divide into 2 broad categories for time series forecasting. So one is autoregressive modeling. So in autoregressive modeling, we say the future value of the time series is dependent on its past value. So there is no external influence which is acting on it, and it's basically dependent on its past value. We say autoregressive, where Y is influencing the next forecasting. And the second thing, which is mostly relevant to environmental application, is forward modeling, where we have an X to Y relationship, where we have an external weather drivers, which basically influence the output. So in this case, we say X is exogenous, which is external influence, and Y is here is the endogenous, where X is influencing by Y output. And so this is the basically 2 time series problem statement. And now if we talk about the approaches which are there, in, so one is channel independent approach. So in channel independent, this is people are using it for autoregressive, where we have a time series which is given to us, a multivariate time series. And the goal is, if you want to do the future forecast of that multivariate time series, we treat each component as an independent, and another is channel dependent, where again, if we have to do a multivariate time series forecasting, we treat each, we take a correlation among all the components. And then we have C and D, where C is basically a subset of B, where we consider the exogenous variables. So exogenous is denoted in white, and endogenous is denoted in orange. So we consider both X and Y relationship in order to do the future forecasting of the Y. And then this is what we are currently working on, where if we know a past X and Y, and if we know the current X, then can we do a better job at doing the prediction of X to Y mapping? So this is what we are trying to target, the category D. And why category D is important for environmental application. So right now, these are the 2 case studies where this is for the stream flow. On the top, we have the rainfall. On the bottom, we have the stream flow. And if we have to just predict the stream flow using existing time series approaches, we can see that we are not able to do all this prediction of the peaks, which is basically dependent on the weather drivers, which is here the rainfall. So if we see the peaks, it mostly corresponds to the rainfall. So for us, in order to do a better job at future prediction of stream flow or any other variable, we have to consider the exogenous variable in this case. Again, second example is for carbon flux, where if we have to do a prediction of the carbon output, we have to consider some of the weather drivers, which basically drives the output for the system. So now I'm going to switch the gear a little bit. I'm going to talk about a seminal work, which is patch TST, which is one of the work which was which shown a very good result as compared to existing models for time series forecasting. And the key component for this model was very simple. So previously, we used to model each numeric value of a time series as a separate word. In this paper, inspired from computer vision domain, they came up with, instead of taking each numeric value, let's take each patch of a time series as a word. We take each patch, and then we treat each patch as a word, and then we feed that into a feed forward into an attention model, and that's all we do. And it retains the local semantic information. It reduces the complexity, and on the result side, we have shown that if we just do the patching, it's able to beat a lot of the linear models as well as the existing transformer-based models, which was prior to this paper coming out. And it basically outperforms the transformer, and it shows. And the future work for this was, can we make sure that there is any cross-channel dependency? And immediately, and this work was came very recently in ICLR 2023. And immediately after that, there was another work which came this year in ICLR 2024, which says that instead of doing each patching, can we take the whole time series as a whole and make it embedding? And then can we do a better job at forecasting? And I'm not going into the results, but the result shows that this approach is more superior as compared to the patch TST approach. But both of these approaches were again an autoregressive, where given the previous Y, can we do a better job at future prediction of future? And then this is another work where they try to use existing LLM for time series forecasting. So they have the weights or model weights for an existing LLM. They freeze the multi-head attention, they freeze the feed forward, and they only change the position embedding and layer norm. With this simple architecture modification, and they just train it on 10% of the time series data which is available to us, they were able to show that indeed existing LLM models, their performance are superior or same as compared to the existing model where we train them from the scratch. This is again another model. I'm not going into detail. And this is the work which we are doing. We are trying to see if instead of just going autoregressive, can we also do an X to Y mapping where we have some previous X to Y, and given the current X, can we do a better job as compared to existing models? So we have in our architecture, this is under submission, 2 different encoders to process 2 different time series. And then we have this cross-temporal modality fusion to fuse them. And then we feed them into a decoder in order to get the future forecast. And in the work, we see that if we are able to do this, and if we are doing 120 days ahead future prediction, then as compared to LSTM and encoder decoder LSTM, which considers both the present as well as the X, and as well as if we see the patch TST, we are able to beat the baseline. And this can, and this was a very small proof of concept. So going ahead, the goal is, can we make a foundation model out of this from a forward modeling where we have both X to Y mapping instead of just Y to Y mapping, which has been done commonly in the other domains. So to conclude, so we have seen different time series scheme for LLM architecture. And the goal is, how can we build a foundation model for the problem of forward mapping as compared to just the autoregressive mapping, which is more useful for the environmental science application. With that, I will conclude. Thank you.
Thank you. Great work. So the biggest problem with using LLMs for time series representation is that they're actually not aware, aware of time. The only component of time series that they capture is sequential aspect of it. So they really represent time as sequence, not without the notion of if you have two time series of different scales, or one is, there's no notion of overlapping intervals or anything like that at all. So with that, one is how do you, I mean, any thoughts on how we actually capture the time series, the time aspect of time series in in all of these architectures? And the other one, the other requirement of using LLM for time series is that all the time series that you're representing are lockstep, same time step scale, or at least well-aligned time step scales, because the n-gram notion, right, has to align. And so how do you deal with then, particularly with exogenous and endogenous factors that do not align on scale?
Right. So your first question is there is no notion of time. So the words are the embeddings is permutation invariant. So to handle it, first is we have some kind of overlap, so between different patches. And the second way to deal with sequential is we add a positional embedding, where with the word embedding, we add another embedding on top of it, which defines the notion of the sequence on that notion. And that's how the same which has been done in NLP. And we have shown that it's not as good as what we want, but it is something which is working fine. And for second question is, how do we handle the different time scale for different exogenous input? So one way which we can handle is we can define different encoder structure or different input embedding for different scales. And then later on, we can have some kind of combination scheme where we can combine them at a later stage after processing them.
Can you comment on the possibility of using foundation model to handle irregular time series?
Foundation model to handle irregular time series.
Yeah, so basically the time interval is not equal. Yeah.
So we have not seen any work right now, and I think because again, I think the problem will be if we have to do some kind of irregular time series for foundation, we have to again take the notion of time, which will be missing if there's an irregular time series.
So what the model showed was you embed the whole time series into a latent space and use that to pretty much just calculate your correlation just between the variates. And that does just work fine. So even if you have, let's say, a differently sampled time series for different variates of yours, you can embed each of them into the same dimensional space and just calculate cross correlations between them and move on. And that was one of the models he showed, and that actually works. Surprising. Does it make sense?
Actually,
yeah, absolutely.
I think in the interest of time, perhaps we can take those questions for the break, and we can now thank the speaker, Kshitij.